I'm Jinjia Zhou from Hosei University. And first of all, I would like to introduce our work. So I will talk about our work about 4 gigapixels per second, 810-bit H.265 HEVC video decoder chip for the AK Ultra HD application. First of all, I have a question. So do you know what's the resolution of your television or your camera? So currently, we have many high-resolution applications for the AK resolution, but the mainstream is still the HD, the high-definition, the 1080p resolution. Today, I would like to introduce our work for the AK, the super high-resolution applications. And so thanks for the new standard, the latest H.265 HEVC standard, it can compress this data a lot. So let's check the image. This is a size for the raw data. So we didn't do any compression. This is size for the raw data. And then we have some standard to compress the data. It is called H.264. It can compress a lot. But recently, we have a new standard. It can compress about 200 times compression. So now it is possible to send this huge data for the AK ultra high definition applications, but at the same time, the complexity is very high. So for the 1080p, the general high definition, here shows the complexity for each pixel. And then if we use H.265, the complexity will be increased. And for HEVC, it will be increased again. And so this is the complexity per pixel. And at the same time, the throughput is increased from the 1080p to 4K to 8K. So finally, we find that for the required complexity, when we normalized, if we normalized the MPEG-2 to 1, the complexity for the HEVC becomes to be 280 times. So our target is now we want to realize the decoder. The complexity is very high, and we want to solve this problem and to realize AK decoder chip. So first of all, we want to analyze why the complexity becomes so high. And here is the challenges for the HEVC. So first, for the component level, there are many components in the whole decoder. But compared to the previous standard, the transform size, you just think about some transform part. It is enlarged. The size is enlarged. And another thing is some modes is increased, and also we add some new functions in the new standard, so it becomes more complex than the previous one. And another one is one of the most important one is the system level. So today, because of a time limitation, so I will only focus on the system level part. For the system level, is because the coding tree unit is enlarged, and also the highly hierarchical size. So what does it mean is, this is a frame. This is a frame. So when we want to decode the picture, we have frame by frame, or you can say picture by picture. So this is one picture. And we divided it into this is a basic unit. We call it CTU. And so based on this CTU, we will further divided to be CU. There are variable size of CU. You can, why is there so many variable CUs? Is because if I'm just stand here, so I'm not moving, it is still image, then at this size, you can use a large block to encode me. So if I'm moving, it means there's some moving parts, several parts. Maybe this hand is in this area, this hand is in this area. Then you need some smaller blocks to encode this kind of moving object. So there are variable sizes in the picture. Then the problem is, so for some components, sometimes the unit is large, sometimes the unit is small, so the speed is different, and we need a large memory to store this kind of pixel and parameters. So compare with the previous standard, we find that the memory space is increased a lot because of the size is increased, and the variable size, the number of sizes increased, and the size itself is also increased. So here is a summarized result. It means we need a large memory size to buffer it. So this is a whole video diagram. So we have many components. They have its own function. And then how to do it? Usually, so this is, you just think this is something called IQ. IQ needs data from this one called callback. And then the result of IQ will send it to IT. So if we always in the sequential way, so it means IQ will wait CABAD, and then IT will wait the result of IQ. So what we do is that CABAD process, for example, process the block 1 or process my digits hand, and then send the result to IQ. When IQ process my hand, CABAD will start to process, for example, process my head. So this means IQ and CABAD can work together. So CABAD finish my hand, and IQ start my hand. And when IQ doing my hand, CABAD will process my head. In order to realize this, we need some buffer. We need some memory. So CABAD, first example is CABAD process my hand and get the result to the IQ. Then IQ need a memory to store the information of my hand. And at the same time, CABAD can start to process my head, and the result will be stored to this buffer. So we need 2 buffer here. And the problem is sometimes CABAD process faster, sometimes it process slow. So for some component, for some special component, only 2 buffers are not enough. So we need 3 buffers here. Sometimes we need 3 buffers. And the size of the buffer is the basic processing unit. We call it CTU. Because HEVC has a very large CTU size, so the buffer size here is very large, much huger buffer size. So it means when you design a chip, you need a large space to store the information. It is not good. We want to have a smaller chip. And at the same time, if the space is very large, the power will be very high. So we usually require low power. So we try to solve this problem, the large buffer size problem. Why we didn't have this problem before is because for the H.264, the previous standard, the CTU size is only 16 by 16. It is a reasonable size, not so big, so it is acceptable for the previous standard. But for the current standard, it becomes very large, so near 13 times larger, then it becomes a problem. And we propose 2 ideas. I may mainly focus on the first idea to solve this problem, how to reduce the buffer. So there are two types of memory in the hardware design. One is called FIFO, first in, first out. Another is called RAM. So for the FIFO, according to the meaning, first in, first out, so the interface is very simple. The first input data will be the first output data. And for the RAM, it can support a random access. So it means for the FIFO, for example, if this is the first input data, it will be output at first. But for the RAM, sometimes we can access the data in the middle. It is a good feature for the video coding. Sometimes we need this feature. And for our design, we propose one called BIBO. So what is BIBO? BIBO can combine the benefits of these 2. So it can make the interface simple, like first in, first out. And at the same time, it can support random access. So what we did is like this. This is the input data. For example, this is all of the data of my hands, and I divided it into several blocks. Then, when we want to put the data into the BIBO queue, it is like this. We divided it into several words, and this is one block, and the words in a block can be written in a random order. Any order is okay. You can choose the order. If, for example, I have 5 fingers, you can just randomly select which finger you want to process first, and which finger you get the first result, and you can put it into the queue. And then, after all of the words are written, you can, the whole block will be pushed. And for every block, it follows the FIFO concept, the first in and the first out. And another good thing is the block can be in variable size, because I mentioned that there are variable sizes for for each component. Sometimes I need a larger one, sometimes I need a smaller one. So here we design a block. It can be in the variable size. And when we read out the thing, the words in block still can be read in random order according to the requirement of the component. You can read it in a random way, and then the block can be pulled after all words are read. And another good feature is that we can merge some block. We can merge some block to be one bigger one. It is also a good feature for some component. So it is example, when we use this BIBO, we can support any types of partitions of the CTU. For example, this is the processing order for this one. So this is just one example. So we divide it into like this, and when we finish the one block, we will push it into the BIBO queue one by one. And for the BIBO queue, the output will be processed first in, first out. So when we pull out, so here we combine many blocks together. At this time, we combine several small blocks to be larger one. And then we also can split one larger block to be smaller one. So now we find that after we're using the BIBO, if the previous component is processed like this, and the current component, we can use this kind of totally different partitions for the next component. And here is the BIBO implementation. So we only need to know the vacancy and the storage of the BIBO, and we can realize the BIBO architecture. Now we replace that triple memory to be the BIBO here to store the pixel. And the BIBO size is according to the definition of the standard. We can choose the BIBO size. And the results show here. So we can reduce a lot when we use the BIBO architecture comparing the triple buffering. And another idea is to store the parameters. So we have two things we need to store. One is pixel, one is parameter. Parameter means some mode, prediction mode. I just briefly introduced the idea. So the key idea is that we use a relay style, then it can sharing some parameters. For example, here, CABAD gets some results. So this is, we combined many smaller FIFOs here, and the FIFO result will be output to the next component. At the same time, it can send to the next FIFO. And then the component and the next component, they can share the information. So for this kind of relay network, this FIFO have three control signals, three sets of control signals. One is for the downstream FIFO, another one is for the processing component, and also the result from this 2 to the FIFO itself. And here shows the result. When we use this relay-based FIFO to store the parameters, we can reduce a lot. This means the FIFO between these two components, it can reduce by 99%. And this means that this FIFO between these two components. So there are still many ideas or proposals for the component level. I will not introduce the detail. So I just want to let you know that to design the whole chip, so we first design every component, and then we connect them together. Today, I focus on how to connect them together. And now we have two ideas. One is BIBO, another one is relay FIFO. So BIBO is here, the orange one. So BIBO is used to store the pixels, and the FIFO is here, the relay network FIFO. It is used to store the parameters. This is a final whole architecture. So we delete all of the triple buffer by using the BIBO and the FIFO. So based on each component, and then we connect them together, and we fabricate a chip using the 14 nanometer technology. The maximum performance is about 4 gigapixels per second at 120 frames per second. Pixel at 120 frames per second. So when we realize the decoder chip, we have the decoder core, and we have a DRAM. The DRAM is used to store the input picture or some big data, and the FIFO and the BIBO is on the chip itself. And this is a different frequency for the decoder itself, for the decoder core itself, and for the DRAM. Finally, we get the power consumption here. This is a core power consumption. It means the power consumption of the decoder chip itself. When we increase it to 8K at 120 frames per second, the power consumption is about 690 million watts. So we compare this work with other results. ICC 13, this work is from National Taiwan University, and this work is from MIT, and this work is also from National Taiwan University. So we can see that compared with all of the other works, we can achieve the maximum throughput, and also at the same time, the power per pixel, we normalize it, the power to each pixel, the power per pixel is smaller than all of the others. And this work is published on ICC 2016, sorry. Here shows a comparison with the other HEVC chips. So this means the maximum throughput. And here is the core area efficiency and the power efficiency and the DRAM efficiency. The larger is better. So we can see that our work is better than all of the others. This is a chip photo, and I have a demo. So this is the AK sequences, and we use our chip to decode these AK sequences. And here is this is our chip, and we have the board to put our chip on the board, and we also have the board to store the decoded chip on that board. That board is the DRAM, and so we can get the result from the chip to check whether our decoded picture is right or not. Of course, we can also check the screen to see whether it is not right or not. Okay, finally, I give a summary. We developed an 8K by 4K at 120 frames per second HEVC decoder chip. It is at least 7.5 times faster than previous chips. And today, I only focus on the system level design. So we propose a novel system pipeline based on the BIBO and the FIFO relays. And also, we did many component level optimizations, and then we combine them together to be the final chip. Okay, thank you. Any questions?
Okay, thank you very much for interesting presentation. I have a small question. Did you face with the pipelining issues? For example, data hazard or structural hazard or control hazard?
Almost no hazard here, no store here, since when we design the size, we mainly based on the worst case, and we test how many, several hundred sequences, almost no store. And for some very small, for some very small resolution, very special case, it may have store for some. But if the resolution is very small, we don't care about that kind of store. So it still can support, for example, very small size, 1080p size. It still can support 1080p at 120 frames per second. There may have store here, but no problem for the small size.
Thank you for your presentation. And I want to ask is about the BIBO queue. Yeah. What's the advantage of random algorithm in your application, and how do you get the wanted data from the random picking algorithm?
So it is because the decoding process itself, sometimes we need some data. Sometimes we need some data from not one by one, not the first in, first out. Sometimes we need a random access some part. So that's why we want to support the random access. And another thing is for the decoder process itself, it needed to divide into many different sizes. This is just one example. There are many different partitions here. So it means, for example, this component, the TU component, the size is like this. And the next time, when we process some MC, it is another component, the size is like this. So the size is changed for different components. So that's why we designed this BIBO, is that sometimes the size can be small, sometimes the size can be larger, and sometimes we can random access some part.
Yeah, okay.
Excuse me. Thank you for a wonderful and interesting speaking. Can you show me the picture that written BIBO and BIBO?
This
yes,
one.
This one, yes. My question is, how do you control the speed of either of them, BIBO and FIFO?
The speed, for example, the BIBO here, the speed of input is controlled by this one called IQ, and the speed of output is controlled by IT. If IT needs some output, he just gets some data from it. And when IT finished some result, the IT will send the data to this BIBO. So the speed is mainly based on this one and this one. If the two have exactly same speed for the same amount of data, then the BIBO can be very small. So there are many space here.
So there are no relationship between BIBO and FIFO? No relationship?
No.
Oh, thank you.
Thank you. Okay. Thank you for the questions. We don't have time. If you have other questions, welcome to ask me anytime.